we're going to continue in 6.1. This set of notes is over basic set operators and Venn diagrams. So a lot of this is going to be just recognizing some notation. Again, math is a language. We use our own notation that you need to be able to recognize, along with introducing this concept of a Venn diagram, which hopefully you've seen Venns before. Venn diagrams are a tool or a visual aid that's used in a lot of things, not just mathematics. Alright, so the Venn, just set it up and remind you what a Venn diagram is. Venn diagram is usually a rectangle with circles drawn inside, and what it is, it's a visual tool to help you represent the relationship between a universal set and its subsets. Alright, usually the universal set is drawn as a rectangle, and the subsets are drawn inside as circles. And again, like I said, it's a visual tool. A lot of things are helpful to understand things visually. Alright, and that's what a Venn diagram allows us to do. It allows us to visualize the relationship between the universal sets and its subsets. Alright, so we're going to start simple here. We'll do more Venn diagrams in later sections where we'll actually do applications where we'll use Venn diagrams to solve with them. We'll do 2 sets and then 3 sets. 3 sets is as big as we'll go. This one here, these are all going to be 2 set Venn diagrams. And again, we're going to use them as a visual reference to what we're talking about. Alright, so a very simple example was, suppose U represents my universal set. So all of the numbers into consideration that I'm looking at are the whole numbers 1 through 9. A and B are subsets of the universal sets, right? Every number in A shows up in U, and every number in B shows up in B. I'm going to draw the Venn diagram using the sets U, A, B, and place the numbers in the appropriate region in the Venn diagram. Alright, so the Venn diagram is a rectangle which would represent my universal set. So this rectangle represents set U. Inside set U, I've got smaller groups, alright, which I'm going to represent my smaller groups by circles. So my smaller group, or my subset, is A. And then my second smaller group, my second subset that I'm looking at, is B. Now, I've drawn them where my 2 subset circles overlap, right? There's this overlap area, and that's because A and B overlap with some common elements, all right? And so this is a visual representation of the square would represent all of the numbers 1 through 9. Circle A would represent the numbers 2, 4, 6, 8. Circle B represents the numbers 3, 4, 7, and 8. And then I put the numbers in the appropriate regions. So and we always start with the Venn diagrams working in the overlap out. Alright, so this overlap here, which we're going to define it later on what its name is, what it's called, represent every number that shows up in both A and B, right? What numbers are in both of my subsets? Well, if I look at my subset A, I've got the number 4, B's also got the number 4, A's got the number 8, and so they share 4 and 8. So 4 and 8 go inside both circle B and circle A, which is inside the universal set, right? 4 and 8 is inside the rectangle. Alright, then I work on my circles, finishing up my circles. So here's circle A, which should be all of the numbers 2, 4, 6, and 8. I've already accounted for 4 and 8. I don't want to do them again, right? They're already in the circle A once, so you don't put them in there twice. And so in this region here are those numbers in my universal set that only land in set A. Well, those would be the numbers 2 and 6. And there's all of the numbers in circle A, 2, 4, 6, 8. Alright, now I do circle B, same thing. I've already got 4 and 8 accounted for, so outside here would be those numbers from my universal set that show up only in B. Well, that would be the number 3 and 7. I'm not done yet because remember the universal set has to represent all of the numbers 1 through 9. I haven't taken care of all of the numbers yet because there are numbers missing, right? I've got 2, 3, 4, 6, 7, and 8. Well, I've got numbers that are not in either of those 2 groups. And so that would be this outside area would represent all of those numbers not in circle A and not in circle B. Well, 1 is a number in my universal, not in my circles. 5 is a number in circle, or not in circle A or circle B, and 9. Okay. And so now I should have all numbers accounted for. If I count 1, 2, 3, 4, 5, 6, 7, 8, 9. There's every number in my universal represented in one of my regions. And again, a number only lands in one of the regions, right? 5 is only in the outside area. 6 is only in the area where set A is. 8 is only in the area where I've got both set A and set B. Alright, so again, there's only one number in each region. Each number is in one region. You don't have them in multiple regions. And there's a simple example of a Venn diagram. And we're going to do more Venn diagrams, like I said. Alright, set operations and the visual representation of them with the Venn diagram. Alright, these are very important that you remember these set operations. Alright, we're going to be using them over and over again in chapter 6, 7, and 8. So make sure that you understand them and can recognize them. Alright, the first one is the intersection. Alright, the intersection of two sets. Alright, a two finite set A, set B. Alright, the intersection is the set of all elements belonging to both set A and set B. Alright, and so I'm going to write my A and B that I used in the last example. So A was the set 2, 4, 6, and 8. Set B was the set 4, 3, 7, and 8. Alright, the notation, and then I'll get to the Venn diagram. Alright, so the notation for intersection is A intersects with B. Alright, and so that's the notation, sort of like an upside down U. Alright, and so what this means, it's every element in set A, and it has to be the same time in set B. It's that overlap, that intersection. And so the word we use here is and. Alright, that symbol represents and. Right, elements in A and B. Alright, so if I go look at my A and B, what elements do they share in common, right? These would be the elements that are in common in both set A and B. Alright, so 4, they share 4, and 8. Alright, 4 and 8 are the only two elements that are in set A and B. Alright, and so represent that with my Venn diagram now. So drawing the same picture, so there's my universal, there's my circle A, there's my circle B. And so that area for A and B, right, this intersection, is this region here, right? That region where A and B overlap. That's my A and B region. Alright, that's where they overlap, right? That's where we would have put the elements 4 and 8. Alright, again, it's where they intersect, right? It's where circle A intersects circle B, which is why it's called the intersection. And the symbol you have to recognize is that sort of upside down U symbol. Alright, so that's the region where A and B intersect. Alright, next one, union. Alright, union of set A and B. Alright, so the union of set A and B is the set of all elements belonging to set A, to set B, or both sets. So basically, it's including any elements that show up in set A or set B. It's all inclusive. Anything that was in A is included, or anything that was in set B was included. If they shared some elements, those are also included. Now the biggest thing with the or statement is we only want to include those elements once. Alright, I'm going to write my set A and my set B that I was using. So my 2, 4, 6, 8. My set B was the 4, 3, 7, and 8. Alright, the notation first. Alright, it's sort of an upside down U. Alright, that is elements in A, and again the word we use is or. Alright, that symbol stands for or. It's all the elements from set A or set B. Alright, and again, making sure not to count anybody twice, right? They share elements, but we only share, there's only one, they share 4, right? But you only include 1 4, right? There's only 1 4 in the real numbers. And so we don't put 2 4s in there, we just put 1 4 in there, alright? So basically the OR is all inclusive. Alright, biggest thing is don't count anybody twice. Alright, so the numbers are 2, 3, 4, 6, 7, and 8, and double check that I've included everybody, right? 2, 4, 6, and 8 are included. 4's in there, 3 is in there, 7's in there, 8's in there. Alright, and so there's everybody from set A or set B. 4 and 8 were in both, but I only put 1 4 and 1 8. There's only 1 8, they just happen to show up in both sets. Alright, so OR is all inclusive. The union is putting together everybody from both sets, right? It's the union of both sets. Alright, so the Venn diagram. So there's my universal, circle A, subset B. And so it's everybody in my subset A along with everybody in my subset B. There is that overlap, but those numbers are only counted one time. So it's everybody in A or B. Right, there's my A or B region. Right, remember, it's the OR, right? All inclusive. OR. One or the other. Alright, that's the union of the two sets. Alright, the complement. Alright, the complement of a set. We like the complement. Alright, well, when we get to the rule of the complement, we'll explain why the complement's nice. Now we're just kind of setting up the notation, the interpretation, and what it means in terms of the Venn diagram. Alright, so the complement goes with a set and the universal set. Alright, so it's a comparison between a set and the universal set. Alright, so suppose I have this subset A. Alright, you representing the universal set, then the complement of set A is all of the elements from the universal, from all of the elements into consideration, that are not in set A. Alright, so I'm going to write down my universal that we've been using. So the universal, if you remember, where the set where the numbers 1 through 9. So 2, 3, 4, 5, 6, 7, 8, and 9. Set A was the numbers 2, 4, 6, and 8. Alright? So the notation first. The complement notation is we put the set with a little prime outside. We call that a prime symbol in mathematics. And what that means is the elements not in set A. Alright, not in set A, but from the universal set. Alright, I can only do those that I'm looking at and look at everything that's not in the circle that I'm interested in. Alright, so for our set, well, A was the even, so not A would be the odds, right? 1, 3, 5, 7, and 9, right? 1, 3, 5, 7, and 9 are all of the elements from my universal that are not in set A. Right? So not in set A, but still from the universal. Alright, so the Venn diagram, so the prime outside is what we're looking for. So the picture, so there's my universal. I'm going to draw it with my circle B and my circle A. So there's circle A, there's circle B. Alright, the complement would be basically everybody outside of circle A. And so everything outside of circle A does include part of B, but not all of B. It doesn't include the overlap that's in A. Alright, but it would be everything outside of A. So it'd be everything outside of A that's in B, and then everything that's outside of both circles. Alright, all of that outside area. This would be the region. That's the complement of A that's not in A region. Alright, the complement. So basically I would exclude anybody that lands in that circle A. Everybody else is fine. Alright, disjoint sets. We like disjoint sets. We'll talk about some rules later on when we have disjoint sets. There's some nice rules. So we like this when they tell us something's disjoint. So since we're going to have applications with disjoint sets, we should know what that means. Alright, so set A and set B are considered disjoint if set A and set B have no elements in common. So there's the big no elements in common. The overlap, the intersection of A and B is empty. Alright, so that means the A and B, right, remember that symbol represents and, is empty. Alright, there's nothing in A and B. It's empty, right? No elements in common. And so there's two ways to draw the Venn diagram. Right? Either you can draw it with the overlap, but then this would be empty, no solution in there, right? There's nothing in circle A that is at the same time in circle B. All right? No elements in the overlap. That would be empty. All right? The overlap would be empty. Or another way we can draw it is if we know they're already disjoint, we basically draw the two circles separate. Right? There is no overlap, therefore we don't draw them with overlap, right? This would be an example of no overlap. No intersection, right? Because it's empty. Right? So we draw them without the overlap. Right? Either way is fine. Right? It just depends on what you're using. But it basically means A and B share nothing in common, right? They have no common elements, right? Disjoint. Oh, that's what you have to remember. No common elements means they're disjoint. Alright, the Cartesian product. The Cartesian product of two sets, set A and set B, is when we're pairing two groups together. Alright, or we're doing two things together. Alright, like flipping a coin and rolling a dice. Right, we're doing two things at once, and I want all of the outcomes. Alright, so Cartesian product is denoted A with the times symbol B, is the set of all ordered pairs. So we write them as a pair because, again, the set is when we group things from A and B together. Alright, that's our new outcome. Alright, something came from A. So remember, my lowercase a would be an element from A, and lowercase b would be my element from B, and we're pairing them together to get a new set. We will do this, especially when we do experiments. We'll pair stuff together, rolling dice, flipping coins, groups of people together, right? We might pair people together. Right? And so whenever we're doing sort of a sequence of things, I'm going to pick something from A and pair it with something from B. Alright, so a simple example, suppose my set A are the numbers 2, 4, 6, and 8. Alright, set B, set B, suppose is, so I'm rolling a dice, and I only pick the even numbers, alright? So my set A is the even numbers for my dice. Set B is, suppose I'm flipping a coin, and instead of writing out the word heads, I'm going to write capital H to stand for heads, capital T to stand for tails, and a lot of times we'll do that instead of writing heads and tails. Alright, so my experiment is I want to roll a dice and get an even number. So my set A are the even numbers 2 through 4. Set B are flipping my coin, getting heads or tail, and I'm going to do set A with set B, and I want to know what are all my possible outcomes. Alright, if I pair A and B together. Alright, and that's what my Cartesian product is. Alright, I'm going to pick something from A and pair it with something from B. Alright, so basically every number in A gets paired with both of my letters from B. Alright, so one option is I roll a 2 and a heads. Another option is I roll a 2 and I get tails. Or I can roll a 4 and get heads. And I can roll a 4 and get tails. 6 and heads. 6 and tails. 8 and heads. 8 and tails. Alright, and there is my Cartesian product. There is all the possible outcomes if I pair set A with set B. Alright, I get a whole new set with my outcomes being a 2 in heads, a 2 in tails, a 4 in heads, a 4 in tails, a 6 in heads, a 6 in tails, an 8 in heads, and an 8 in tails. And there, if you count them, there are 8 outcomes, which is where its name comes from. Alright, if you think about it, I paired the 4 numbers in A with the 2 letters in B. Well, 4 times 2 will give me 8, and so I had 8 outcomes when I pair those two together. Right? I have 8 pairs where I pick something from A and something from B. Right? And so that's where the name Cartesian product comes from. Alright, make sure you understand this. This is very big. Alright, the set operations for union, intersection, complement. We will be using those terms and symbols over and over and over again in the next chapter and the chapter after that. So again, make sure you understand these basic symbols and rules and what they mean, as we'll use them in chapter 6, 7, and 8. Alright, next examples, we're going to look at some basic, or what we call common examples of these operators for union, intersection, and complement. Alright, and so that's where the next video will pick up.